So that is the technology, and then come within technology, fabrication. Right? Fabrication of things, making of some designs. So these are the two approaches. One is called bottom up. So you have to build up and go high. So from the raw material you are building up some structure, and this is top down. So you have some big thing, and from there you remove material in appropriate fashion to create the design you want. That is what these artists do. So this is called top-down approach. Yes. I'll be talking of iron beam nanofabrication because my beam, remember that the cantilever, that was created by iron beam. So I am now coming there. So essentially you have an ion source where you create ions, positive ions, and then this is some accelerator mechanism in which you accelerate it, and then after acceleration this energetic ions fall on this material, the basic building block. Right? You have some, you go with some kind of a mild steel block in the mechanical workshop and then give a design that by cutting, shutting you make this structure out of this steel block. So that block is here, main block is here, and using this iron beam make some modifications there and create a structure out of there, out of that. So that is known iron beam induced manufacturing. And essentially these are the two processes. One is called nuclear energy loss, one is called electronic energy loss. These ions, when they are going and hitting that target material, they can hit at the ions in the material, the nuclei of the material, target material, or they can just hit the electrons. And it turns out the same ion, incident ion beam, if the energy is low, right, we have accelerated it through some energy. So if that total energy, final energy is low, the chances are more that it will hit the nucleus. It will dislodge an atom from its position. But if the energies are high of the incoming ions, chances are they will leave all the ions at their own places and only affect electrons. Okay? So higher the energy, this side, mega electron volt type of incident ions, you only affect the electrons of the material. Whereas if you are in kilo electron volt range, if the incoming ions are of kilo electron volts, then they affect mostly the nuclei which are sitting in the target atom. They dislodge that. Now this is the kind of thing, this is the incident ion particle coming into this material, and this is the collision cascade region we say. In this region it is making its own changes, effects. So the ion is coming here, going here, scattering and hitting many of other ions, and finally it stops somewhere in the material. So then there are secondary collisions. This atom has been dislodged from here, and then this goes and hits this atom, and then this is dislodged, and then some atom goes and hits here. The primary ion is here, okay, but all these secondary collisions which are cascade, that is why called cascade. So at certain stage some of the surface atoms can come out. This is known as sputtering, right? This is an important phenomenon. You can take out material from it by bombarding with iron. You can take out material from there, right? And then there are other things. You get X-rays and you get electrons, and all those things are there. The instrument that I am using is called focused ion beam, and it's a tabletop apparatus. Of course, the cost is still high, some 4 crores, 5 crores. When we purchased, it was 4 crores, and now the dollars have gone up, so I believe it should be around 5 crores or so by now. So this in focused ion beam, you take ions, and the acceleration is not very high. It is still in few tens of kilo electron volts, but then it can be focused. The arrangement is there to focus. Focus in the sense that finally when the ion beam will fall on the material, the size of the beam would be, in our case it is optimum, which we say, which they call optimum size, that is 7 nanometers. Right? So you can focus it down to 7 nanometers. And from that you can remove the material, sputtering. Right? So back. So for removing the material, what you do? For removing the material, you use this type of thing. Right? What is called here? I also call it kurpi. That's why I written. So you make it fall on the soil, and then it takes out the material. Right? So what you have is here is some how much 5 centimeter type of kurpi, and what I have 4 crore rupees of kurpi. The difference is it's not 5, it's not 7 centimeter, it is 7 nanometer. The size of this kurpi is that. And you can do something else also. You can also stack material, right? So the same kurpi, after removing the material and after putting that plant, what does gardener do? From the same kurpi it will bat and put some whatever urea or other things, and then it will stack it there. So you can put material, you can remove material. Both things you can do with the 7 nanometer kurpi. And then the third is imaging. Imaging. You also have an electron beam, and that electron beam is part of scanning electron microscope that is built in this apparatus. So whatever is going on there by this 7 nanometer beam is to be seen, and for that seeing, this imaging thing is done by this electron beam. So that's the schematic work. Yes. Next. This is a photograph of that tabletop apparatus called FIB, focused ion beam. So it has energy can go from 500 electron volt to 30 keV. It's a gallium ion. Somewhere it is written gallium ion beam spot size. Oh, this is electron. This is electron. Right. This is electron. Beam size is 1.1 nanometer. This is FIB, gallium liquid metal ion source. 5 keV to 30 keV. This is the current, and beam spot size 7 nanometer in optimized conditions. Right. Terms apply. Right. So 7 nanometer, but then terms apply. You don't get 7 nanometer, you cannot sue the company that I am not getting 7 nanometer because the terms apply in the optimum conditions. Yes. So this is that another. This is for imaging, in fact. Yeah, go ahead. This is sputtering. This is milling, nanoscale milling. So the beam is coming and taking out the material. So sputtering. Yeah, back. And typically, this is a crucial parameter. Typically, to remove 1 micrometer cube of material, you will need about 1 second. So don't think to make 1 millimeter by 1 millimeter by 1 millimeter trench using this 7 nanometer film. Your whole tenure of BTech BE will be gone into making one trench. In 1 second, 1 micrometer cube. So when we are making the design to be fabricated by FIB, this is an important parameter that your work should be finished in 5 minutes, 10 minutes, 1 hour, half an hour, 15 minutes, not 100 hours or 1000 hours. Yeah, next. And this is how I put the material, right? How I add material to this. So if you have to add some material, we have facility for adding platinum, tungsten, and carbon. So some kind of a gas is injected containing that material, organometallic gas, and that is flown over this substrate, that material, and then this beam is sent from top. The beam does 2 things. If it is a organometallic gas containing platinum, this beam, this ion beam, by hitting that, will crack the molecule of that gas. and the volatile part will go away and the platinum will be there, and then this beam will make a bond of that platinum with the lower material. So that is how you will stack platinum. You can deposit platinum or tungsten or things like that. So this is that deposition scheme in FI.